Start. Alright, so welcome back. Welcome back to this YouTube channel. So in the last video, we have looked at what fixed. I think in the last video we have looked at fixed to fixed, probably cycle GAN. No, I think we have looked at. I don't actually remember what video have done. Sorry, Pro GAN. Yeah, in the last video we have looked at Pro GAN, progressively adding more GAN, like more layers. So we have looked at that technique to actually increase the performance of a GAN, like to predict a image belonging to a specific distribution or a specific class or a specific distribution. It's a very good word. So in this video, we are going to look at another another GAN, which is called as super resolution GAN. So as the name suggests, it's a GAN that you use to actually increase the resolution of an image to make a blurred image as a high quality image. So that is the idea. So that is the idea. So we are going to use like this. We are going to build a CNN model, or we are going to. I think generator is a very good word. We are going to build a GAN to actually take this blurred image. We're going to build a GAN to actually take this blurred image and create it to be a high quality image. So that is the idea. So how can we do that? Well, of course, if I introduce this problem to a person who is like into deep learning, he might suggest us to actually use a CNN, and that is actually the right answer. We are going to use a CNN, but of course, because we are also going to use the adversarial loss, just for the absolute fact that we want our model to actually make that image look realistic. So for that, we're going to use GAN model. So that is what this paper is released. I don't know when, but this is released. So all right, so we are going to use this model for doing that. So this paper is released, right? Nothing is actually new with this, but as you can see, so these are some sample images. So here 4x2 specifies that we are going to use a 4 upsampling layers. All right. So this is the output of SR GAN. This is the output of our super resolution GAN, and this is the original image. And as you can tell by this looks, like it is pretty much similar. Both of these are pretty much similar. So therefore, we could say that SR GAN did perform pretty well, right? So these are some outputs. So this is the actual value. I think we have got this image by performing some type of interpolation or something. I don't know. Yeah. Yeah. So we have got this image, and they have also used a metric called I think it is called PSNR. I don't know what that is. I'll probably look up when we go down. So we have this is the blood image, and it has a PSNR of 0.64. Okay. So again, this PSNR is not. I don't think it is a very good it doesn't evaluate the performance of this model that good, but because here this blurred image has got higher PSNR than this good image. So again, it might not be a very good validation metric, but still okay, we're going to use it. So here we have used a SR ResNet, so a super resolution ResNet. I think we'll just use a GAN model, of course, but we're not going to implement the ideas that are that will be proposed in this paper. I'll go through the ideas that are proposed in this paper in just a few minutes. So this is the output of the SR ResNet. Pretty good, but still, as you can see, there is a lot of blurring, and then there is a lot of blurring. And if you look at the output of SR GAN, of course, the PSNR value is lower than that of the ResNet. I don't poor. I think it's a little poor evaluation metric, but still it works. All right. So for this image, the output of the SR GAN is actually very is top quality, and there are very final details that are also being tracked, right? The hands and all that. It's actually pretty good, and then the surroundings are also visible, right? And then the original this is the original image, and as you can see, there are some similarities between the SR GAN's output and this original output. And then you can see, right, Yes, there are patterns that have been tracked, but still there are some misconceptions like this and all that, right? Yeah, so this is like rounds and rings, and this is pretty much this, because if you take a blurred image, and there could be like many more possibilities of the output, right? There could be um many patterns or many types of images that we form, many patterns that you can form in the output image. We don't know what that is because we're going to average over that. Essentially, blurred image is actually taking, let's say, 2 pixel values and averaging them. It might create some blur. That is actually blurred image. So there could be many more possibilities. Looking at this input, we could draw it. Let's say a human can draw it with many possibilities. So therefore, we will not expect the GAN models output to actually be exactly similar to the original model output, but we want GAN to actually sample it better. So that is the reason why we are actually using GAN, right? We are using GAN just to make sure that the image is realistic, right? So all this very useful things they have told, right? So again, I'll go through the loss function. You might see the word VGG network here. I'll go through that what that is. So as you can see here, pixel wise averages of possible solutions. As you can see, let's say this is the blood image. There are actually many possibilities, right? There are many possibilities. That is why we are using GAN based models to actually like select one probability, right? Select one image that could be probably the output, and then we'll use adversarial networks to actually determine how realistic that image is. Again, very good. And again, with this, like all the other GAN network that we have looked at, here also loss function is the main thing that is proposed in this model. Loss function is the main thing. So I'll probably go through whiteboard. Okay, we don't need whiteboard. I'll explain it like by ourselves. So I'll go down. So this is the architecture. This is the architecture of this model. So this is the generator and this is the discriminator. So the generator is going to predict an image, and the discriminator is going to take this image, and it is going to predict whether the like generated image is real or not. And we'll also have these real values or real images, and we'll pass the real images to the discriminator, and we'll predict will then and the discriminator will predict if the images are real or not. That is the idea. So we'll first train the generator. So this is the generator. Generator takes in the input. It has like 9 kernels, 64 sorry 9 by 9 kernel with 64 kernels instead of one. And then we're going to follow similar patterns, and we're also going to have skip connections, just like residual network. We're going to have skip connections, just to make sure that variants don't like gradients don't vanish. So, and then we're gonna have B residual blocks, and plus just a bunch of CNN layers, right? 3 kernels, 3 by 3 kernels, 64 3 by 3 kernels, 256 3 by 3 kernels, and stride one. And then we're also going to perform something called pixel shuffler. I'll tell you what that is. So pixel shuffler is nothing but, so let's say you have a like 256 by 3 by 3. Then what we are going to do is we are going to just shift these values, and let's say it's a like 3-dimensional block. Think of something like a 3-dimensional block or something, or probably a cube, right? So think of a 3-dimensional cube. So what we'll be doing is, given a cube like this, maybe we are going to increase this value, right? We're going to increase the depth, and just reduce the number of channels, or reduce the width or depth. That is what we are doing here. We are going to shuffle these pixels just to make sure they are in correct shape. And then we'll perform some other convolutional models, and after performing the final convolutional model, we'll get the actual, or we'll get the output. Again, we are going to use patch GAN. Yeah, we're going to predict patches. We're going to predict patches of these images again. So this is going to be LSR, like low resolution, just for the notation purposes. In this paper, LSR is nothing but the image generated by this generator. No, G of LSR is the LSR is the like image generated by the generator, and LR is actually the actual input to image to this generator. And then we'll also have this discriminator which will take in this LSR and some other real values, and is going to predict, like for each image, it's going to predict whether it is real or not. And we want the discriminator to be fooled. So generator wants the discriminator to be fooled to actually predict this image as real. So that is the idea. Again, the discriminator, we're going to also have a bunch of convolutional layers. So we're going to have like 3 by 3 64 3 by 3 kernels, and 64 3 by 3 kernels, and many patterns are followed here. We'll also have stride 2 just to downsample this images just for downsampling these faster, right? And this is like the actual architecture, nothing new, right? So just we have this classical CNN architecture that we have looked at upon probably many times, hundreds of times. So now we'll get to the main part, the main thing that make like the main specialty. I could say this is the main specialty of this SR GAN, right? So we are going to use so this is going to be a loss function. So the main thing is the loss function, right? So in this loss function, we're going to have two terms, or two terms is not the right word, but we're going to have two addables, or two parameters, right, or two values that we'll add together. We'll have the content loss and the adversarial loss. We're going to add content loss and the adversarial loss. I'm going to get to what they are in just a minute, so just stick with me. So okay, so like this is for the, so we're going to just look at what this is. So first we'll have the content loss. So let's look at what the content loss is. So the content loss, again, as you can see here, LSR, the low resolution MSE, sorry, super resolution MSE is equal to just like forget all of these terms. The main thing is like this is the main thing. This is the main thing that we would care about, like right now. So we'll subtract the high resolution image. So we'll just subtract all of these pixel values. So we're going to take this high resolution image, the original high resolution image, and we're going to subtract the values of we're going to subtract the pixel values of the GAN. So we're going to take the GAN, right? So we're going to take the GAN and we're going to pass in this low resolution image. We're going to pass the low resolution image to this GAN, and then we're going to take the high resolution image, the actual output high resolution image, and we're going to subtract both of these values, and then we're going to square them and get the mean, right? Just like a mean squared error. You're going to just find the like pixel differences, nothing new again. So that is the like the main, that is like LSR MSE. So this is like the first part of the content loss. And then we don't have this, the next part is actually very important. So this is like classic, like normal things, right? So just we're going to loop through all of this width and height values. So for every pixel, we're going to loop through every pixel. So that is what both of these summation functions are. And then we're going to get each pixel values of the actual image and the predicted image, and we're going to subtract both of these values and square them and find the mean. We are squaring them just to make sure that terms don't cancel out, right? And then the next loss function is, right, so after we have predicted the output image, right, think about it, rather than just subtracting both of these values, rather than subtracting the pixel values, how about we find the features, the actual features that are found by the model on both of these images. So let's say you're taking the high resolution image, the actual high resolution image, and the image predicted by the model, right? So we have this predicted image for the high resolution image and actual high resolution image. So how about we pass them through a model, let's say a powerful model, and then get the features that are tracked. So just like understand what features are tracked for each of these inputs. So we can understand what are the features that are tracked for both of these inputs, and maybe subtract them. So that is the idea. We'll get the feature vectors, right? So like we have the CNN, right? So we'll get all of the weight values in your language, in our language. We'll get the weight values or all of this. So we're going to have a CNN, right? All of these values or all of these patterns that are found in this middle of the CNN, we're going to take them, right? We're going to input an image and we're going to take these outputs of these feature vectors, and we could just subtract both of these feature vectors, right? When we pass the input high resolution image and the predicted image. So that is what we'll do here. I'll just go through this little mathematical statement for you. LSR VGG equals, we're going to loop through again all of these pixel values, right? And then what we'll be doing is, so this is the, so this symbol, I don't know what that is. I'll just probably search it. Just give me a minute. What that is. P, yeah, PHI, yeah, yeah, whatever that is. I'll probably say VGG. So yeah, um, yeah. So this is nothing but, as you can see here, I'll just read through for you. We define the VGG loss based on the ReLU activation layers of the pre-trained 19 layer VGG network displayed in the Simonian and Zisserman with phi ij. We indicate the feature map obtained by the ijth convolutional after the ith max pooling layer within the VGG network, which we consider given. So basically what we are doing is, so this is going to be the VGG model, and we're going to pass this VGG model. We're going to pass the high resolution image. So first we are going to pass the high resolution image, the actual image, to this VGG model, and we're going to get some features as output. We're going to get some, let's say, features as output. So essentially, what we'll be doing is, weights is not a very good word. I'll take back that word. Weights is not a very good word, but I think like just take a VGG model and at the final layer add a CNN layer. If we could just add a CNN layer, the final layer, and get an output, we'll get a feature representation. We'll get a feature vector. We'll get a feature vector based on that image. And then what we'll do is, we'll take this feature vector of this image, the high resolution image, and we'll also get the feature vector of this generated image, which is the SR image. We're going to take the feature vector of this generated image, right? So we're going to pass the low resolution image into this generator, and then we're going to get the feature vector of that generated image, and we'll just subtract these values and square them and get the mean. Essentially, we're performing the mean squared error, not for the pixel values, not for the direct pixel values, but for the outputs of feature vectors. So we're going to get the feature vectors, the pre-trained VGG. So let's say we'll use pre-trained VGG and get the both of these like feature vectors, and we can just subtract them and just find the difference between them. So that is the main part, the content loss. That is the main thing actually. And then this SR GAN. So we have the adversarial loss, just like just like what we had earlier. So this is the values. So d theta is the output of the generator. G is the output of this discriminator. D is the discriminator and G is the generator. My bad. And then we'll just add all both these values and use it to actually update our generator. So we'll have this generator updated based on these values. So that's it. Nothing actually new, right? Nothing big, but like this, like research is going on. This is a very good research paper. I think this is a pretty old one. No, not pretty old, but yeah, comparatively older. 2017, right? A pretty older paper, but get the idea, right? So the basic idea is, if there is a blurred image, there could be many possible ways it could be interpreted. That's interpreted. It's a very good word. So what we'll do is, we'll just pass that with generate GAN network, just to make sure that we'll produce an image that makes sense and also is of high resolution, and it is similar to this actual image, what it represents. And then what we'll do is, rather than just performing the MSE, we will perform the pixel wise MSE, but we'll also add another factor or another main thing. Okay. So rather than just doing the MSE, what we'll perform is, we'll perform this function. So we'll pass in this image, the high resolution image, original image, through this VGG and get the feature vector representation. And we're going to subtract that by this output of this generator, the feature vector representation of this output of the generator, and we could actually find the gradients, and the generator could update this value such that the features that are tracked both in the original and the real are similar as possible. So thus the VGG, the generator can get trained better, can get trained better. So that is the idea. So thank you for watching. That's it for this video. In the next video, we'll code it in TensorFlow as always. So thank you for watching, and I'll see you in the next video. So